All right, good hot afternoon. So we learned about a really very useful rule, as you shall see for the rest of the semester, and that's Huckel's rule, namely that 4n plus 2 cyclically conjugated systems, so they have to be cyclic and they have to be conjugated, they have to overlap contiguously, are aromatic. They enjoy special stabilization. They are relatively stabilized relative to their open-chained analog or anything that disrupts cyclic delocalization, such as an inserted CH2 group, which acts basically as an insulator, if you think of it as current. And this is reflected not only in thermodynamic stability, but as it turns out also in relative kinetic stability. They are relatively unreactive. And therefore, a lot of aromatic molecules occur in nature, particularly benzene, the aromatic molecule par excellence. It's all over nature. Nature obviously is smart. It deals with molecules that are stable, sufficiently stable in an oxygen atmosphere in our atmospheric conditions to survive. Conversely, we also learned that Huckel developed a counterpart series, namely that with 4n electrons. So 4n plus 2, that seems to abstract, is basically 6, 10, 14, 18 increments of 4, starting with benzene 6, okay, in a simplified way of looking at it. The anti-aromatic series 4n is multiples of 4, so it's 4, 8, 12, 16, 20, and so on. Those are destabilized by resonance. The electrons do not like to interact, and they prefer to weasel out of it if they can. So some cases we learned that they couldn't, like cyclobutadiene. That thing is so fixed to really distort it sufficiently to prevent delocalization would cause a lot of sigma strain, too much sigma strain. And so it just tries to twist a little bit, and it tries to bond alternate by stretching two bonds so that the two double bonds stay away from each other as much as possible. But this is all to no avail. It's anti-aromatic, so it's destabilized by conjugation. And indeed, the experimental results show that this is a bad camper. Okay, it's very reactive, very air sensitive, deals all the dimerization. It dimerizes at just a few degrees above the absolute zero in Kelvin, and so on. Then you jump to benzene, and that, relatively speaking, is rock stable. And then we went on to cyclooctatetraene. That guy could weasel out of cyclic delocalization by adopting a tub configuration, which is actually enforced by the sigma frame. You can't flatten a cyclooctatetraene without breaking your molecular model. Some of you may have tried it. So that, and it's perfectly happy doing that. Okay? So it just pops up, and as you saw in the model on Tuesday, there the pi frames of neighboring double bonds are orthogonal. They're perpendicular to each other, so overlap is basically disrupted completely. And then we looked at 10-annuline, and then 10-annuline was iffy because there was disruption by for steric reasons for the trans one isomer where the two hydrogens pointed to the inside, and the others had bond angle strain and other problems. But then after that, the series, actually starting with 12, pretty much alternates between aromatic and anti-aromatic, as established primarily by NMR studies, but also by some chemistry. So this is an extremely useful concept because it allows you to compare two structures and say this one should be more stable than the other. It will also allow you to say something about the feasibility of a structure being formed by whatever mechanism, elimination, rearrangement, what have you. If it leads to an anti-aromatic compound, it's unlikely to occur, or it occurs only with difficulty. And more useful is when it leads to an aromatic compound, there's clearly a driving force. Particularly anything that leads to a benzene, as we shall see in 20 minutes or so, is great. Okay? The system really loves to have the cyclically delocalized electron sextet. Moreover, this applies not only to carbocycles, as we shall see, it also applies to heterocycles, where one of the carbons or several are replaced by heteroatoms, such as a nitrogen or an oxygen and the like, and we'll come back to that as we go along, particularly in an organized manner in chapter 25. And you can extend this to charge systems. Okay? It doesn't matter basically what it is, it doesn't matter which atoms are in it. If you have a cyclic delocalization of 6 electrons, that is a stabilizing feature, or 4n plus 2 electrons in general. And so charge systems are best illustrated actually by looking at our first example here, cyclopentadiene. Cyclopentadiene, as it turns out, has an astonishing pKa of 16. As you may remember, 16 is water, or an alcohol. That's the pKa of an alcohol. Alcohols are acidic because oxygen is very electronegative, right? And yet there we have a CH bond that it has this kind of acidity. Compare this to propene, as we did in the first lecture this semester, it's about 40. So there's an incredible dropping of 24 pK units in the system. Now you may argue, okay, propene is monoallylic, this is bisallylic, and so there's more resonance possible. So propene dropped from propane by about 10 units, so maybe this bisallylic system should drop by another 10, should be around 30. But this is still way off 16. Okay? 30 would be around an acetylene, about 35 or 33. So this means that with potassium tertiary butoxide, you can pull out this proton. Okay? Tertiary butoxide is tertiary butanol has a pK of 18. So your equilibrium constant will be 100 towards the anion here. So why is that? And the answer is aromaticity. Because when you pull off this proton, you leave behind 2 electrons. And these 2 electrons can delocalize over the ring. There are 5 resonance structures. I'm only showing 3, where if you start with the electron pair up here, you move it in here to make a double bond here that pushes this electron pair here, or you can move it in here and here, as I did for this resonance form, that puts the negative charge here, and then you can do it again, that puts the resonance, the electron pair rather, here. And as you keep on going, there is one resonance structure for each carbon bearing a full negative charge, meaning, since they're resonance forms, that the molecule is completely symmetrical, and it bears 1/5 of a negative charge on each carbon. And if you now look at the electron count, it's 2, 4, 6. So often this is indicated by the circle, although we'll try and stay away from these circles and draw proper resonance forms. But the point is that at 6 electrons in a cyclic array, it's aromatic, 4n plus 2. So it's like a negatively charged lower analog of benzene. Okay? So charged or not, doesn't matter, okay? As long as there's 6 electrons in a cyclic array. Conversely, the cyclopentadienyl cation is terrible. Okay, so this is just switching charge from negative to positive. When you do that, you take away 2 electrons, and the system becomes a 4-electron system. And you can see this by making bromo or iodo cyclopentadiene, where you have a leaving group sitting here, and that leaving group doesn't want to leave for the hell of it. Even though formally it's bisallylic, and we already know monoallylic undergoes SN1 reactions, so bisallylic is even better, and it is indeed in an open chain system where this bond isn't there. That would solvabilize very, very rapidly. But once you close the loop, it doesn't want to leave, and the reason it doesn't want to leave is because putting a positive charge here, which is equally delocalized as the anion, makes a cyclically delocalized cyclopentadienyl cation, and there the electron count is 4n. 4 electrons, anti-aromatic. Doesn't want to be that. Okay. You can go to the next higher one, playing the games that we played in the anilines, cycloheptatrine. And there's actually a history to this. Around the turn of the past century, people made cycloheptatrine, and they knew it was an allylic type system, so they tried to do an allylic halogenation with bromine, and there was a reaction, but they couldn't figure out what the product was because the product was a salt. And that puzzled people for decades, okay? Until Huckel's rules came about, and they realized what is happening is bromination occurs, so you have a bromine sitting here, and that bromine immediately takes off to make a cycloheptatrinyllium cation, also the short term is tropylium, and that is delocalized, so you can write 7 resonance structures that puts plus charge on each carbon, so there's 1/7 of a plus charge on each carbon, and if you count up the electrons, it's 6 electrons again. But now, as a cation, a positively charged analog, higher analog of benzene. And to finish this off, you can then look at the acidity of this guy, which would put a negative charge here, like this material here, the cyclopentadiene, and the acidity of cycloheptatrine is terrible. It's way up there, 39. Actually back to where propene is, but this is bisallylic as we just figured out, so this guy should be around 30, but it pops back up to about 40. Okay? So the acidity of cycloheptatrine is worse than the acidity of an analog of this, where, for example, you have removed one of these single bonds or removed the double bonds, some open chain analog. And the reason is that it's the cycloheptatrinyl anion. It's got 8 electrons. That's 4n anti-aromatic, so it doesn't want to form. So this is a very nice, very simple rule that allows you just looking at a structure, as long as it has a cyclic delocalization, you can just count up the electrons and say, okay, this one should be unusually stable, or this one should be unusually unstable, or it should just be normal if the structural distortions don't allow for cyclic delocalization. Yeah?
What's the mechanism for getting rid of the hydrogen on the 7 members to left?
The mechanism of getting rid of the hydrogen, you mean going from left to right? Yeah. Bromine. It's a bromination. Okay, so instead of getting, so it's an allylic bromination, but instead of getting the allylic bromide, the bromide takes off and makes a salt. There's the bromide, so you get Br minus and the positively charged tropylium. So this is reminiscent, of course, I mean, it's an SN1, but typically an SN1 of an allylic system, you start with the allylic halide or allylic something that has a leaving group, and you go to the cation that's higher in energy. It's a reactive intermediate, which is then trapped by a nucleophile like water, and you get the allylic alcohol, right? In this case, it's not going up, it's actually going down to the SN1 intermediate. The SN1 cation is actually a stable species that is more stable than the starting halide. Okay? So that drives home the point that aromaticity has a great stabilizing feature. So we can go to more elaborate systems, and in fact, the sky's the limit. So I'll give you another simple rule here. Oops. That deals with polycyclic hydrocarbons, for which you can write all kinds of structures. And I urge you, when you have time to doodle as you're waiting for the bus, or your boyfriend or girlfriend, or have nothing else to do, just start drawing structures. In fact, this is a very useful exercise because it reminds you of things, it gives you practice, and it keeps your mind sharp. So naphthalene, for example, the rule actually, so one can look at all these polycyclic benzenoids, and there are many more of all kinds of with all kinds of topologies. The good approximation to simplify you how to count electrons is to just count the peripheral electrons, because typically these guys, if they have a 4n plus 2 or 4n outside circuit of pi electrons, they're either aromatic or non-aromatic. So if you count naphthalene, you can see it's 10 carbons in the periphery, 10 electrons aromatic. This guy, anthracene, if you go around the loop here, it's 14 aromatic. Tetracene is 18 aromatic. If you go around the bend here for phenanthrene, it's again 14 as you count them all up. And this is true for all of them, actually. They're all aromatic. Maybe not surprising, they're all made out of benzene rings, okay? But there are situations where if you start messing with the framework such that you incorporate 5-membered rings, or 4-membered rings, or even 3-membered rings, the circuitry may change, and the electron count may differ too. Here's a case that is slightly more complicated, right? We have 4 benzene rings fused in this odd manner, and so here the peripheral electron count is very useful, because as you go around the bend here, around the loop here, 2, 4, 6, 8, 10, 12, 14. 14 is aromatic. Okay? And so what happens to this double bond? In fact, it's what's called isolated double bond. It just sits there, and it's basically discriminated again. It's shunned by the outside loop, because all molecules try to develop aromatic circuitry, as it were, for obvious reasons. Nature knows that if I accentuate, in this case, the outside loop, I'll be fully aromatic, and that's good. So the double bond in the middle is just sitting there and got nothing else to do. Here's another case where we have 3 benzene rings fused to an internal benzene ring. You can think of this as 3 benzene rings connected by a single bond, or you can write another resonance form where you have double bonds across here, here, and here. And again, it's useful to count the outside periphery, the circuitry on the outside, and it's 18 electrons. That's also aromatic. So whichever way you do it, it's aromatic. So that peripheral count rule is very useful, and it'll get you there in almost every case. And I won't give you exceptions unless they're easily solved in an exam. Okay, so now even more interesting, for polycyclic systems, you can have also charges, and indeed multiple charges. So for example, if you look at this beast here, that guy's called pentylene. It's another one, like cyclobutadiene, another one of those molecules that people thought one should be able to make, but people couldn't make it for decades and decades. Only in the last 2 decades that people have been able to make derivatives, and then actually also make the parent, and the parent is extremely reactive, similar to cyclobutadiene. It undergoes Diels-Alder reactions, other cycloadditions, reacts with oxygen, polymerizes. Very unstable. Why? Because here now we use the peripheral rule. It's 8 electrons in a cyclic loop. Okay? and that's 4N, anti-aromatic. And here, unlike cyclooctatetraene, the molecule can't twist out of the way, out of conjugation. That bond here, remember this is basically cyclooctatetraene where you've taken 2 hydrogens away and made a bond across the 8-membered ring. Now that fixes the molecule, it flattens it, okay? And it can't get out of it. Okay? And so it forces the 8 electrons to interact. So we can, on the other hand, make an analog of this, which is this as a dianion. And the simplest way to do this is to actually start with this molecule here, which is a simple triene. It just happens to be a branch triene, okay, where instead of having 3 double bonds in a row, one of them just sticks out of this carbon here in this direction. But otherwise, it's bridged, but that's irrelevant. But if you look at it differently, you can look at it as a cyclopentadiene on the left and another cyclopentadiene on the right. You realize that the hydrogen should be acidic, because like cyclopentadiene. And indeed, you can pull out the first hydrogen, just like in cyclopentadiene, and remarkably, you can deprotonate with base also the second ring, even though the neighboring ring is now negatively charged, because you're making a 10 pi aromatic dianion. And you get the 10 electrons because you have 2, 4, 6, and you're generating 1 electron pair here by deprotonating, and another electron pair here by deprotonating, and that adds up to 10. And that's 4N plus 2, and that's aromatic. Okay? So this really is a dianionic equivalent of naphthalene, which also has 10 electrons. Okay? So as a take-home practice examples, I'm giving you these 3 guys, and I'm asking you, what are these? Okay? This guy's called benzocyclobutadiene. I was actually involved in making this. This guy here has a bridge in the center. There's a hydrogen coming off, so this is an sp3 hybridized carbon. And this guy here is also quite famous. It's called azulene because it's got a deep blue color. Okay? So what are these? Aromatic, non-aromatic, anti-aromatic. And to finish this off, again, to emphasize this is a very important concept, 300,000 papers in the last 30 years. So that's 10,000 a year, basically, on just that subject alone. Okay? So this is an ongoing bit. Okay, so much for Huckel's rule. Now that we understand how to get at a designation of aromatic and anti-aromatic and non-aromatic, let's go back to benzene, which is the most abundant aromatic molecule in nature. Here it is again. And we said that it has 30 kilocalories resonance energy, aromaticity. That's due to the special delocalization. And we said that this, in this case, translates into unusual lack of reactivity. And that's true. But it's not unreactive. In fact, nothing is unreactive. You can always find some reagent that will perturb the peace of some entity that's sitting there dormant. I mean, even noble metals, noble elements have been reacted. Things like neon and argon and krypton. It's all a matter of what you fire at them. Okay? And so in the case of benzene, clearly, by far the most prevalent reactivity, if there's any, should be electrophilic attack. Because benzene is a ball of electrons above and below the molecular frame. An electrophile, which would be blue, if you remember the color scheme, would see a lot of red, and like the red flag, and it would just go for it. Okay? The electrophile is the bull, and the benzene is the red flag. And indeed, one can do electrophilic attack. Surprisingly, and as we shall see, actually not surprisingly, instead of addition of an electrophile, we get electrophilic substitution. That is termed electrophilic aromatic substitution, often abbreviated EAS. So what happens is you take benzene, and you take an electrophile, and it will react to displace one of the protons, or exchange a proton for E+, and introduce a substituent into the benzene ring. This is obviously extremely useful, because it allows you to functionalize benzene rings. And so synthetically, that's paramount if you want to make all the benzene molecules that nature has made, and then analogs for medicinal purposes, and so forth. And the trick is to find an electrophile that's just hot enough that it will do so. Okay? So we learned that normal HCl in aqueous solution is not hot enough. We learned that bromine, ordinary bromine, is not hot enough. These are reagents that would react with a normal double bond, such as ethylene or an alkene in general, by addition. Okay? You need a hot enough electrophile to affect this, and instead of addition, you get substitution. Those are the 2 differences. What's the mechanism? The mechanism is actually quite straightforward. The first step is an old hat. The double bond comes out, attacks the electrophile, and makes a bond. That leaves a positive charge here. That's the first step of the Markovnikov addition in all kinds of electrophiles adding. This positive charge is delocalized, so we can write 3 resonance forms, plus charge here, a Lillich transposition puts the plus charge here, another Lillich transposition puts the plus charge here. These 3 resonance forms, where we have a relationship of all the plus charges sitting at position 1, 3, and 5, it's always a 1-3 jump, we will see ad nauseum in the next week and beyond that. It's always the same. Okay? So, the fact that there's resonance at this intermediate actually explains why benzene reacts at all. Because in the first step, what you're doing, and that explains why it's relatively unreactive, you have to disrupt the benzene aromaticity. And that's 30 kcals. 30 kcals is a hell of a lot of energy to climb up on. And typically, in addition to activation barriers that have to do with the electrophile itself, it would give you prohibitive activation hills, okay, where you would have to go to 200-300 degrees to affect the reaction. What saves you is that, indeed, the intermediate is also delocalized. So it is somewhat stabilized by resonance. Nowhere near as much as the 30 kcals of benzene, but by a Lillich resonance. And remember, Lillich resonance was still worth a few kcals for each resonance form. So that saves the day. Otherwise, benzene would indeed not react at all. And at this stage, so we're repeating these 3 guys over here, there is a difference between addition to a normal double bond and what benzene does. In a normal double bond, that positive charge would be trapped by the nucleophile, X-, okay, that's sitting there.